All right. Now, ladies and gentlemen, oh no.
Questions, any comment on the presentation so far?
Before we ended, we had looked at
The presentation is somehow clear.
Okay, that's good.
To what we call
Others, Sister Prudence, what do you say so far? You have any question?
That when we follow these notes that's in lecture 3,
Sister Prudence, are you okay?
I just wanted to go through it now, more of revision for you, and it can help us to understand more. So this is on which page? It is on page. It is on page 31.
Irene, are you okay?
Page 31. You open your notes. You will see that part of the specification of stating class.
Okay, fine. So let's proceed with examples. In this example, we have a linear transformation. This is a transformation because we have, it takes things from error 2 and it returns things to error 3. So this linear transformation is defined.
Now, what I'm saying is
this linear transformation is defined when you give it two vectors in R2, x1 and x2. It works on them like this and it returns vectors in R3 given by that. So we want to find a matrix representation of T with respect to bases. So this is the B is the basis for R2 and B prime, which has B1, V2, V3 is the basis for R3 and U1, U2 is this. Yes, please.
The noise in the background.
Oh, my noise in the background. Sorry. I'm sharing an office room with someone and he's also doing a lecture, so I'm sorry, I can't do anything about it. Sorry, Irene.
Okay. Okay, please.
Please bear with me. Okay, this one I'm going out. Okay, so this is what we have. We want to find a matrix representation of T with respect to these two bases. So this is what we do from the formula for T, the way T is defined, then T of U1 gives us 1, -2, -5. How do we get T of U1? Our U1, remember, is 3, 1. So it means T of 3, 1 is going to be 1. You get, yeah, it is 1 because this is x1, the other one is x2. And okay, so the system is warning me we have 10 minutes to go. Hopefully I could have finished this example such that I reschedule another meeting. So the U1, it is 3, so it returns 1 here. This is minus 5 times 3, which is minus 15 plus 13. So this gives us -2. This is minus 7 times 3, which is minus 21 plus 16. That one gives us -5. So TU1 gives us this, TU2 gives us that. The next thing, we express these ones, these images as linear combinations of V1, V2, V3. So you see, this is an image of U1 under T. This is an image of U2 under T. So since this image is in W, it means that this image can be written as a linear combination of basis elements in R3. So the basis elements in R3 are V1, V2, and V3. So we write TU1 as a linear combination. So K, V1 plus K. So this is the linear combination, but the V1 is this, V2 is this, it is that. So we are interested in getting the values of K1, K2, and K3. So when we equate coefficients, then we definitely get K1 minus K2 equal to -1. We get K2 plus 2K2 plus K3 equal to -2. We get minus K1 plus 2k2 plus 2k3. So we get this system of equations. When we equate coefficients, we get this system of equations. And when we solve them simultaneously, we have k1, k2, like that. So we do the same to, so it means that when we write TU1 as a linear combination, which is that, which is 1, V1, and so on, it gives us that. So the column or the matrix of representation of U1 is this column here, which is that. We do the same for U2. We write the U2 as a linear combination of vectors V1, V2, V3. So it gives us that. It gives us this system which solves to this. So it means the T U2 is also this matrix here. Remember, this forms a column in the matrix representation that we are looking for. So it means the matrix representation TBP, which is A. This one for 1 becomes a column. This one also becomes a column. So we have it as that. So this is the matrix of representation for the other transformation. Above. Okay. Any question on this example 1?
No.
Okay, so fine. Let me reschedule another meeting. Okay, it is giving me 5 minutes. I think I can go through example 2 in the 5 minutes before we break. So example 2 is a linear operator because we are mapping things from P2 to P2. We are mapping things from P2 to P2. And what is P2? P2 is a vector space of all polynomials of degree less or equal to 2. And so it is defined by T. When you give this transformation T, a polynomial Px, it returns P of 3x minus 5. It returns T.
I need to find out. Okay.
It returns a polynomial.
You go to page 31.
Px, P of 3x minus 5. That is, give it a polynomial in degree 2. A polynomial of degree 2 is of this form. So it returns where there is x, it replaces x with this 3x minus 5. Where there is x, it replaces it like that. A constant comes as a constant, then where there is x, we have that. So we want to find the matrix representation of T. We want to use the matrix representation of T, compute this, and then after we compute this directly, we can compute this directly just to check whether our working is okay. So here we go. From the definition of this, we have this. So T of 1 is a constant, so this one gives us 1. Remember, when you have T of this, so it means T of this constant C naught, it returns C naught since we don't have an X. So that one is 1. Then T of X, because we also have X, because the basis, we are following the basis. Remember, the basis for that polynomial, the standard basis is 1, X, and that. So what we are doing, we are writing the basis elements here. We are finding the images of these to get the here. Then after that, we write the images as linear combinations of this. So the T of X gives us where there is X, we put 3x minus 5, and T of X squared, where there is X, we put 3x minus 5 squared, and that one gives us that. So when we write T of 1 as a linear combination of the basis elements, is T of 1, which is 1. So we can write 1 as 1, times 1. Sorry, this is an error. We need to correct this error. This should be 1, not negative 2. So it is 1 times 1, then plus 0 times x, plus 0 times x, then plus 0 times x squared. That one gives us 1, so we get this 1. Likewise, this tx, 3x plus 5 written as a linear combination of the basis elements in T2, so it is negative 5 times 1, which gives the negative 5, then plus 3 times x, which gives 3x, then 0 that, so it gives us that. Then tx squared, this is, we can write it as a linear combination, 25 times 1 plus minus 30 times x plus 9 times x squared. 9 times x squared, so it returns this, and then we get this as the matrix of the transformation. We get this as a matrix of transformation. Then it means that this one B is the same as this matrix of transformation, then times the P of B. So the P of X, this is the polynomial we want to get. So its P of B is its basis, which is 1, 2, 3, which is that. And then when we multiply P of B times that, we get this. So these are the coefficients of the polynomial, and so it gives us that. How do we compute this directly? We just substitute where there is x, we put 3x plus 1, and when we simplify this, it takes us to this. So you see, this is the same polynomial, meaning that our answer is right. Okay, any question on example 2?
Yes,
Where do you feel we need to explain on example 2?
Yes, yes, sir.
Yes.
66, negative 84, and 27.
Okay, let me read it. Here, you tell me where.
How do you get those figures? Those 64, negative 83?
Okay, so the idea is, we said work out this transformation to get the image of this polynomial. We get the matrix of transformation B, then times the vector PB. The vector PB is the basis for this. So the basis for this, or not the basis, we just pick out the basis, then we get the vector. So the TB is the matrix that we got, which is this one. So when we multiply it by